Everyone, and thank you for the introduction, Henry. So today I'm going to talk about neutron powder diffraction. And first of all, I wanted to show you an outline of the presentation. I will start with a little reminder about diffraction. Then I will continue by defining what a powder is, powder diffraction, and some of its applications. Then I will explain the Debye-Scherrer configuration to obtain the powder diffraction pattern and also what information can be obtained and how, paying special attention to the Rietveld method. After this, I will present one of the applications of powder diffraction with the material is not an ideal powder, and we can determine the texture of the preferred orientation of the crystallites. And then I will discuss advantages of using neutrons with some examples. And finally, I will present some of the powder diffractometers that we have at the ILL. So diffraction is defined as the process by which a beam of light or other system of waves is spread out as a result of passing through a narrow aperture or across an edge, and is typically accompanied by interference between the waveforms produced. So the historical perspective of diffraction, definition of crystallography, etc., were discussed in Larissa's single crystal diffraction seminar. So if you were not able to attend this seminar, I recommend you to have a look at her presentation if you want to have more details about that. In diffraction, we have an incident beam coming from the source and a diffracted beam picked up by the detector. And the wave has a certain wavelength, and the angle at which diffraction occurs is designated by theta. If the wave from the top path, reaches the detector at the same point along the wavelength as the wave from the bottom path, there is constructed interference, and a peak is produced when the intensity is plotted as a function of 2 theta. However, if the waves reach the detector at different points, there is destructive interference, and all we get is background. So in order for the bottom path wave to reach the detector at the same point along the wavelength as the top path, the bottom path must travel some additional integer and multiple of wavelength compared to the top path. So the wavelength, the d-spacing between crystal planes and theta are related by the sine function. Lambda is equal to the d-spacing times the sine of theta, and as this only takes care of half of the additional length that the wave must travel, the total distance is 2 times the d-spacing times the sine of theta, which gives the Bragg's law. And diffraction peaks will occur only at those angles where the Bragg's law is satisfied. Okay, so now before explaining the technique of powder diffraction, it is necessary to know what a powder is. And a powder is a polycrystalline solid composed of a large number of crystallites of micrometer length scale. And ideally for powder diffraction, these crystallites in the sample are randomly oriented in such a way that some of them will satisfy the orientation necessary for diffraction. Typical sample volume used is around 1 cubic centimeter, but this depends a little bit on if we use X-rays, neutrons, or whatever. And some of the most important reasons for studying powders are that, first of all, not all materials can be prepared as single crystals. A large number of powder preparation methods exist, and they can be prepared in large quantities. Then many materials in the real world are generally polycrystalline, and therefore it's interesting to study their properties. And powder diffraction provides information not only about the single crystal structure, but also about the microstructure, the orientation of the crystallines, or phase identification, among other applications. So in powder diffraction, the basic constraint in order to see the Bragg peaks in diffraction is the Bragg condition. So we need to have the crystallite oriented at an angle where the Bragg's law is satisfied for a given d-spacing. And the diffraction pattern can be obtained in different ways depending on the nature of the sample. So in order to obtain a diffraction pattern, or in other words, to see many Bragg peaks, we can do the following. When doing single crystal diffraction, it is necessary to scan the monocrystal through many different angles in order to recall all the diffraction pattern. Another way is using a broad range of incident wavelengths, which is known as the quasi-Laue diffraction, and this was also explained by Larissa. And finally, the powder diffraction pattern can be ideally obtained in a single shot using a sample having a broad range of crystallized orientations, which is the case for powder diffraction, as I already mentioned. So the main difference between single crystal and powder diffraction is shown in this figure. Since powder samples contain crystals oriented in many different directions, the incident beam finds the same plane oriented in many different directions, so that the beam is diffracted in all directions, obtaining what is known as the Debye-Scherrer rings, or Debye rings. And here you can see the differences between the real space and the reciprocal space lattice for single crystal and powder diffraction. Just remember that we are taking into account only elastic scattering, so the incident and the scattered wave vector has the same energy or the same wavelength, and only the direction is modified. And again, the wave vector can be defined with the sine function as k times the sine of theta. Sorry. As in the real space, it is necessary to multiply it by 2 to take care of the total distance and not only the half of it. So for a single crystal, which is represented here by the blue color in the real lattice, we can obtain the reciprocal lattice where each point corresponds to a family of planes with a given d spacing. And if we consider a powder formed by 4 single crystals, represented each one with a different color, it is possible to see that the same family of planes is diffracted in more than one direction. And as the number of crystallized in the system increases, the circumference becomes clearer, and its circumference will correspond to a family of HKL planes with a given d spacing that diffracts in all the directions. So with this slide, I just wanted to show some of the many areas in which powder diffraction is used in chemistry, physics, condensed matter, pharmaceutical science, life science, biochemistry, material science, geological science, or archaeology, among many others. And therefore, it's a multidisciplinary technique that offers a powerful tool for the characterization of many different materials. So, coming back to this figure, diffraction in powders occurs in all directions for each Bragg angle to theta, because there is a random distribution of crystallized orientations. So for that reason, powder diffraction arises in cones, and the intersection of these cones with the detector form what is called as the Debye-Scherrer rings, as I was mentioning before. So the Debye-Scherrer configuration is shown in this figure, and we have the incident beam, which is diffracted by the sample in many different directions with different intensities, and we can have front or back reflections. The detector used is a banana detector, and every spot of a circle formed by the intersection of the cone with the banana detector corresponds to the same plane in many different orientations. And although the cones, although the cones correspond to a circle in the reciprocal space, what is shown in the banana detector is the intersection of the circle with the detector and not all the circle. Then these cones are recorded on a point or a position sensitive detector, and the resulting information is plotted as intensity versus diffraction angle diagram. So the powder diffraction pattern contains a lot of information, and one of the main applications of powder diffraction is the phase identification, or what is known also as the fingerprint of our sample. And usually the main phase can be easily identified from the position and the intensities of the peaks. However, secondary phases may be harder to recognize because there aren't enough peaks to identify the phase, or there are some phases that can come from impurities or other reasons. Then the reflection or the peak positions are determined by the lattice, and we can obtain information about interplanar distances, for example. Then the peak intensities are determined by the nature and the coordinates of the atoms in the unit cell. And finally, the peak shape and the width of the peak are determined by instrumental effects, for example, the optics of the diffractometers that we are using. And also we can see the deviation of the real crystal from an ideal one, such as crystallite size, lattice defects, or whatever. So the Rietveld method for the analysis of powder diffraction data was a breakthrough because before that, the diffractogram was analyzed by fitting each individual Bragg peak. However, what the Rietveld proposed is to refine the crystal structure instead of fitting the observed diffraction pattern directly, because the peak positions are determined by 6 parameters, the dimensions and the angles of the unit cell, and the peak intensities are determined by the position of the individual atoms. So, in this method, least squared refinements are carried out until the best fit is obtained between the entire observed powder diffraction, not only single peaks, and a calculated pattern. So different models for the crystal structure, diffraction optic effects, instrumental factors, or lattice parameters are simultaneously refined. And how is the analysis carried out? So first of all, the diffractogram of the static powder is collected, which can be called our measurement. And then the intensity profile is calculated as a function of 2 theta angle for a model whose structure is close to our studied material. And the goal of the Rietveld refinement is to get a calculated diffraction pattern as close as possible to the one recorded by the diffractometer. And this is done by minimizing the residual Sy, which is defined as the sum of the square of the difference between the observed and the calculated intensities. And in order not to give more weight to those peaks that has higher intensity, a weight is assigned to each peak and is defined as the inverse of the observed intensity. So, in order to validate the refined crystal structure, there are different parameters that should be taken into account. The first one is the weighted profiler factor, and this is the most meaningful one from a mathematical point of view, because the numerator is the residual minimized in the refinement. So for the same reason, it is also one that best reflects the progress of the refinement, because we are doing iterations varying the different parameters that define our powder. And then the expected weighted profiler factor is the equivalent to the weighted RWP, but the numerator is considered as the expected value coming from the number of refined parameters, P, the number of data points, N, and the number of constraints, C. Then we have the Bragg factor, which is based on the Bragg intensities, but no, it's not based on the Bragg intensities, but on those deduced with the help of the model. And it serves as a useful function because it is sensitive to misfits in the pattern that do not involve the Bragg intensities of the phase or the phases that we are modeling. And another useful numerical criterion is the goodness of the fit, and it can be useful to check how adequate is the model that we are using when the value is much higher than 1, for example. So that means that the model is not fitting well our data, or if it is smaller than 1, it may mean that the counting statistical errors far exceed the model errors, either because we have poor counting statistics or because, for example, we have very high background. So for real materials, the powder diffraction pattern shows not only the crystal structure, but also shows microstructure details. And this is the case of the texture of or preferred orientation. So as I indicated before, the ideal sample for powder diffraction is composed of many crystallites randomly oriented. But what happens if they are not randomly oriented? What if they have a preferred orientation? Can we still perform powder diffraction? Yes, we can. And actually, powder diffraction is a powerful technique to determine the texture of materials, which can be defined as the deviation from randomness of the distribution of the crystallite orientation in our powder sample. There are basically 2 parameters that have a strong influence on the orientation distribution of crystallites. One is the number of crystals, which ideally should be large to have random distribution. And the other one is the external shape of the crystallites. And well, an increase on the anisotropy of the crystalline shape is translated into a decrease of the randomness due to the orientation of crystals in one direction. So it is important to study the texture of materials because the orientation of crystallites has a profound influence on the physical properties of materials, such as the strength, the Young's modulus, electrical conductivity, etc. And they depend on the properties of single crystals, but also on their orientation distribution. Therefore, quantitative texture analysis is many times essential in the investigation of new materials, to study the anisotropic behavior, to optimize some application that we want to optimize for any material, and to see how the properties of this material varies as a function of the direction. And an ideal powder, which has all the crystals in random orientation with respect to some sample direction, this ideal powder will scatter equally in all directions. However, crystallite orientation will increase the intensity of reflections that are in the orientation, in a given orientation that is overrepresented, we could say, and will decrease all the reflection, obtaining an even intensity due to texture, which is what I explained before. So the texture of a sample can be measured through what are known as Paul figures, and to do this, the radiation source and the detector must be aligned at the proper angle to have diffraction from a given family of planes. And once the system is aligned, then the sample can be rotated about these alpha and beta angles, and the intensity is recorded. This allows the two-dimensional representation of Paul figures. And basically, a Paul figure is a two-dimensional representation that shows the variation of the intensity with the angles alpha and beta. And this intensity recorded at a certain sample orientation is directly proportional to the volume fraction of crystals that are in the diffraction condition. And finally, the full three-dimensional representation of texture is given by the orientation distribution function, which can be achieved through the evaluation of a set of Paul figures or diffraction patterns. And this orientation distribution function can be defined as the volume fraction of crystallites or grains oriented along a certain direction that it's generally called G. Okay, so I have explained in a general way the powder diffraction technique, and one question that might arise is X-rays or neutrons. So the answer always is that it's better to use both of them. And actually, neutron powder diffraction is generally used after having some X-ray data because we can obtain it with lab instruments. So it's always good to have a previous idea, and it is many times necessary to have some beam time in large scale facilities to justify why you want to study this or this. However, there are some clear advantages when using neutrons that derive mainly from the interaction with matter. And we all know that X-rays interact with the electron cloud, and neutrons interact with the nucleus. So disadvantages are that neutrons are sensitive to the presence of light elements. In particular, neutron powder diffraction is very important for the localization of hydrogens in the structure, because hydrogen is a strong neutron scatter while it's one electron, so it's not very visible by X-rays. In addition, adjacent elements in the periodic table have very similar electron scattering power, while they can scatter neutrons very differently. And therefore, adjacent elements can be effectively distinguished using neutrons. Then isotopes have different scattering lengths, and this is especially important for the localization of hydrogen through deuterium substitution. And since the scattering of neutrons is weak and the absorption is usually low, they have high penetration depth, and this makes them excellent to study big samples and using complex sample environments such as high-pressure cells, furnaces, etc. Then the coherent neutron scattering length does not depend on the scattering angle 2 theta. And in the case of X-rays, the atomic scattering factor has a sine theta over lambda dependence, and this means that at high 2 theta angle, Bragg peaks in X-ray diffraction patterns will have lower intensities, while for neutrons, the Bragg peaks have similar intensities over the whole pattern, and they depend only on the crystal structure. And finally, the neutron carries a magnetic moment, and this makes it an excellent proof for the determination of magnetic properties. So now I will give two simple and practical examples about the usefulness of neutrons. And the first one is about neutron isotopic substitution for the localization of hydrogens in metals. So for hydrogen in metals, neutron diffraction is a very powerful technique because we can localize hydrogen or deuterium atoms in the lattice. And usually upon hydrogenation, there is a reduction of the symmetry with an increase of the lattice parameters while the hydrogen atoms going on specific sites in the crystal structure. But there are some metal hybrids that, like this one presented in this example, that keep their symmetry. And in these figures, the X-rays and the neutron powder diffractograms of these species with deuterium, this one with deuterium atoms, are presented. So we see that the relative intensities of the X-ray powder diffraction patterns are the same for both species, and the only major difference is that the pattern for the hybrid sample is shifted to the left. And this is what we expect for an alloy that experiences an increase of its lattice parameters, but keeps the same crystal structure. However, we cannot get any information about the localization of the hydrogen or the deuterium atoms in the crystal. But for the case of neutron powder diffraction, the two diffraction patterns are quite different. Similarly to the X-ray pattern, in the case of the hybrid, the peaks are shifted to the left compared to the original species, let's say. However, it is clear that the relative intensities are completely different in the two patterns, and this is due to the contribution of deuterium atoms to the neutron diffraction. So, sorry. Okay, so another advantage of neutrons is that they can detect ordering in its crystal structure, and this is another good example. It can be concluded for the, so we have this alloy of iron and cobalt, and it is clear from the X-ray powder diffraction that is cubic, but is it a body center qubit where cobalt and iron are randomly distributed, or it presents a structure like CSCl, which is with one atom at the center and the other one at the corners. So the simulation of the X-ray powder diffraction pattern is clear that both patterns are identical, and due to the X-ray scattering contrast, the low X-ray scattering contrast between iron and cobalt, it is impossible to distinguish the two structural models. But if we look now to the calculated patterns from neutron diffraction, here there is a clear difference between the two patterns arising from the high contrast between iron and cobalt scattering lengths. And the correct structural model of CSCl could be easily identified. So finally, it is worth mentioning that there are a wide variety of instruments with which powder diffraction can be done at the ILL. And these instruments can give access to different resolution, different sample sizes, different measurement techniques, such as time of flight or a variation of the theta angle, etc. And you can find many details on the ILL website with all the characteristics of each instrument, which should be consulted to know which is the most suitable instrument to study your powder. So thank you very much for your attention, and thanks also to Henry and Gabriel for the discussions about, of the presentation, and also if you have any questions, feel free to ask.